Thank you for, yes, thank you for, oh, sorry, what something, okay. Thank you, organizers, for inviting us to give a talk. It's actually a great honor for us to give such a talk among the group which is active in control under communication constraints, which is a very recent and active field. And we started started research almost 15 years ago in this area, and actually we didn't have a chance to speak to the experts in this area. So maybe it's first chance to talk to qualified people. And we had divided our presentation into two parts. I will be speaking about mostly theory, and Boris will be speaking about simulation and applications. So, and actually, as I told, this new area was born about the beginning of this century, first years of the century, and end of the previous century. And there are famous and actually classical works in these areas related to the famous data array theorem. This theorem was invented by several groups in the world in almost same time, and actually it was a start of a sort of renaissance of cybernetics from my point of view, because cybernetics was defined by Norbert Wiener as a science of control and communication. And soon after the beginning of cybernetics, this control and communications area were separated, and they were separated almost for half a century. And now they are more close than before. And it is very important now to study this new area with new tools which were developed during this half century. So here you can see some classical works, pioneer works, and some survey works, and the book by Matveev and Stavkin is also now a classical book, I think. So we started with Boris at about year 2005, when we were visiting Rob Evans in Melbourne in October for 2 months, 15 years ago, now already 16, soon will be 16 years ago. We stayed with Rob Evans, who was already active in this area with Girish Nair, and they are closely related to this data array theorem, which is presented here. And it's this result and other results in this area where they looked as a final result, necessary and sufficient conditions. And the question was what to do if everything is already solved, like the great Russian physicist Lev Landau, Nobelist, used to tell that all beautiful girls are already married, and all good problems are already solved. So this is was the situation when we visited Melbourne, and one thing was discovered by us, that these results, necessary and sufficient conditions, was obtained with coder of a big complexity. And complexity of the coder, the memory required for the coder, was growing if we want to get results, the error close to the optimum conditions, close to the necessary conditions. And this is good for theory, but not good for practice. And we decided to do something practical with more simple coders. And next slide shows the background we had, pacification method, which allowed to get necessary and sufficient conditions for pacification, for existence of feedback passivity system, existence of feedback making system passive. And this is for linear systems, of course, but we are interested in nonlinear systems also, because for linear systems all was already done. So I need to mention the minimum phase conditions, something with connections. No, that's okay. Minimum phase condition and hyper minimum phase conditions, which is minimum phase with symmetric and positive high frequency gain. And now we the result actually I'll show you briefly that under this hyper minimum phase condition, this hyper minimum phase condition is necessary sufficient for existence of bilinear solvability of bilinear inequalities, matrix inequalities, which are equivalent to existing feedback making system passive, strictly passive with respect to the specified output. And under these conditions, it's also possible to find the gain, feedback gain making system passive. It is proportional to the output matrix for the specified output, and the coefficients, the gain should be sufficiently large. So the coding procedure which we used, of course, the first line is a simple static coder. It's not enough. What we were using, we use a first order coder at the beginning, and the coder range was assumed to decay exponentially to the limit value m infinity, and the central number is updated with the first order rule. Deviation signal, and this deviation is transmitted over the channel. The system we were considering, where we studied the problem of master-slave synchronization. Actually, is closely related to state estimation, and the slave system with control can be interpreted in many cases as an observer. And the nonlinearity should satisfy the sector conditions, and it makes the problem more simple, but not too simple. So we have master and slave system. Slave system can be controlled, and we want to design such a controller which can be stabilize or pacify system under communication constraints. So we have communication channel with a limited capacity, and coder is on the transmitter side and decoder on the receiver side. And the question is how small can be done synchronization error with static output, with a static output feedback. Here in the epsilon bar is signal error which arrived through communication channel. So we use the Lyapunov function, quadratic Lyapunov function. It's natural since we have a passive system. We use the storage function for a passive system. And we made the function, the inequality for V dot in such, with the parameter mu here, which is chosen as large as possible. We, of course, cannot find the tight bound, but we can try to find as large as possible. So for some, we know that for some mu, such inequality holds under hyperminimum phase condition for linear part, but we use maximal possible mu, and it can be evaluated too. And the result is that limit synchronization error is overbounded with value proportional to the transmission error, which depends also on Lipschitz condition for nonlinearity. For Lipschitz constant is here, and the value of k, the gain k. So it's not very good estimate. It's rather conservative. But what is important is that this transmission error delta is inversely proportional to the transmission rate. And for such a simple coder, we can evaluate sufficiently good estimate for this transmission error. And the result qualitatively is very clear that limit synchronization error is inversely proportional to the channel capacity R. So it cannot be made arbitrarily small, but the bigger the channel capacity, the smaller can be made the error, synchronization error. This was the first result. It was published in the Physical Journal, Physical Review in 2006, and we were very enthusiastic and decided to extend it and to understand better the whole field, because it's not so good that we cannot make arbitrarily small synchronization error. For linear system, it goes to 0, but for nonlinear, it doesn't go to 0. The question is why? Can we change this situation? And this situation can be changed if we transmit not the signal of the master system, but the error. In the case of transmission of the error between systems output in this structure, the results are qualitatively different. Qualitatively different. The same coder allows us under practically the same assumptions allows us to obtain a different result. Now, for this case, it is important again the value eta in the Lyapunov inequalities or passivity inequalities. This eta can be actually choose arbitrarily close to the stability degree of the numerator of the transfer function of the linear part. So if we know the transfer function of the linear part, we can choose parameters of the gain in such way that this eta can be arbitrarily close to eta naught, which is stability degree of numerator. So, and this eta naught is a very important number in this case, because the result is as follows under the previous conditions, and for k satisfying passivity relations, and with the choice of the coda parameters rho and t satisfying some inequalities. What is important then is that rho is not is less than 1, of course, but it is not sufficient, cannot be very small. It depends on the eta, on this parameter eta, which cannot be large. This is most important inequality here. And choosing the coda range exponentially decaying with decay rate rho, the result is that for any initial error, the error is decaying exponentially, and is also bounded for all t. And this is very important that in this situation we can achieve the same result as for linear systems. The error can be can go to 0, but it cannot go to 0 arbitrarily fast. This is also important. The limited decay rate depends on the properties of the linear part of the system, of the Luria system. And almost the same result, similar result can be obtained for state estimation problem. For pacifiable Luria system, we design a nonlinear observer, which is embedded to the coda. And the estimation error, state estimation error, again, goes to 0 exponentially. And this results was published in the year 2009. So these are two main results in our study for several years. And also we studied the adaptive case, a case when we do not know some parameters of the system. It was very interesting for us to study adaptive case because we were working in the area of adaptive control for several decades. And for adaptive synchronization problem, we studied Luria system again with unknown parameters theta, non-linearities, several non-linearities additional can be present here, and it is assumed that only the output of the system can be measured, and we need to design controller or adaptive observer. You can interpret it differently, allowing to achieve the small synchronization error with communication channels of limited capacity. So we used the adaptive observer, which was used by us before. It looks like that, tunable observer with theta here, theta hat are tunable parameters, adjustable parameters, and this is output injection term here. And adaptation algorithms was used using pacification approach for speed gradient methods. I do not go into detail. It's Lyapunov-based approach, actually, and with some robustification in the adaptation algorithm. And with this adaptive observer, the results is rather cumbersome, but it's was obtained actually. Again, we assume that linear part is strictly pacifiable, and is pacified with this gain matrix of observer. This is important, and some additional regularity assumptions, Lipschitz conditions, and boundaries for nonlinearities should be valid. And then there exists constants C1 and C2, such that for arbitrarily delta, under some choice of design parameters alpha and gamma, depending on delta, we can guarantee that synchronization error limit synchronization error is less than delta x for delta x determined by delta. So it is proportional to the specified value. For any delta, it can be delta. So synchronization error can be made arbitrarily small. It cannot, we cannot prove that it goes to zero, and I'm not sure that it goes to zero really, but it can be made arbitrarily small. And this delta is actually delta x. Synchronization error is a proportion to the transmission error. Again, it depends on the transmission rate inversely proportional. So we can make it arbitrarily to make it arbitrarily small. We need to have an arbitrarily large channel capacity. So, but it's not very nice result, but actually I do not know other results in this area for adaptive case, adaptive system. I would be, I would appreciate if somebody knows some results on adaptive controller or adaptive state estimations under limited capacity communication channel. So again, this hyperminimum phase condition allows to design observer, not it's how to design observer under this for nonlinear systems. It's not very old results. It actually formulated by Denis Yefimov and me in the year 2006, about the same time. And also these results were extended later in a few years. So we presented them the IFAC Congress in Milano in year 2011. And later we published a paper in Automatic and Journal already with extended version where bounded disturbances were included. So if we have disturbances acting to both master and slave system, then we cannot hope for decaying error. Error cannot be can go to zero if we have bounded disturbances. So in this case, we also obtain estimates depending on the level of disturbances. Limit synchronization error depends also on it is proportional actually to the level of intensity of the disturbances. Okay, and this is basically the end of my part. I outlined for you some results on based on pacification approach to synchronization and state estimation, and for Laurier nonlinear systems with nonlinearities in sector bounded, and for limited capacity communication channel. So passifiability conditions was very important in all this research. Future research actually, what we were doing later was more closely related to practical problems, for application problems, and some examples. And Boris will be speaking now about examples. Thank you very much. My part is over. I stop my demonstration.
Thank you. By the way, there is one question from Sasha in the chat. I don't know, maybe
yes,
you can already.
Yes, we were awaiting for a question from Sasha, because his results, which were shown a week ago on the restoration entropy, may be related in some way. But the question is, even more, the estimation error will vanish as t goes to infinity. Can you comment on how far your scheme beyond this approach in terms of channel capacity? Actually, I cannot make a precise comment. I just may suppose that the schemes are actually different. It maybe need to be more carefully investigated. So the results are indeed different. But I should say that these results were published 15 years ago. So it's not surprising that later results are better.
Yeah, it's clear, but my point is that you assume that you measure only the output.
Yes.
But under your condition, the decoder can reconstruct the whole state. And to use
yes,
this information is necessary.
Reconstruct state is good thing, but we have a channel transmitting only
no,
scalar.
No, I mean locally, the decoder can reconstruct the whole state without any communication, and then to communicate this estimation. So the decoder can solve the problem of state estimation locally, and then to use this information in order to transmit the estimate via the channel.
So you suggest to transmit the whole vector, not a scalar output.
Yeah.
If you have errors, that may be a problem. So these errors will go through the channel. I'm not sure how it will work, how you can achieve the vanishing error.
Yeah, sure, if there is no disturbance.
Yeah. So there is some relations. Maybe we need to think about it. And Daniel also comments that there could be some computational limitation on the encoder to prevent it to reconstruct the state. Maybe, yes, encoder. We didn't consider the limitation, the complexity of coder and decoder. Probably it depends. It's important, I think.
Okay, I think there is one more question in the chat from Alexei.
Above?
Yes, above Daniel's.
Aha. Just a moment. Oh, so long question. Alexander Pogromsky, I catch only the last part of the question. Now I read the first part. Under the HMP condition, the coder can estimate the whole state locally. But you already said that locally, as fast as one wishes. Locally, yes. The same holds in the adaptive case.
I may retranslate my question. What is the informal physical sense of being passive? Could it be stated in general words?
Could you say it again, Alexei? Physical meaning of passivity?
Yes, yes. You name your approach as passivity based, and so I suppose that it would be instructive to catch the informal sense. What is the key point of your approach, being passive?
For linear systems, for example, output feedback passivity means that its numerator of the transfer function has a maximum possible degree, and it is Hurwitz. So it's minimum phase and with the maximal possible degree. Or there are different terms in. No, it doesn't matter. So it is just a system which is easily to stabilize. Maybe I don't know if it's a good explanation for you.
But from the physics point of view, I think that it rather means that there are no internal sources of energy in the system.
If
it is incapable of, say, self-exciting, something like this. Is it a correct point of view?
You know, for physics, this interpretation, system without internal energy sources, it is for a system without control. If we control the system, then we may insert some energy and take away some energy by control. And so this interpretation for controlled system is, how to say, it's not instructive. Because for physics, we know we have how to say, the conservation laws, like conservation of energy and other things. And this area, it's a boundary area between physics and control. I call it cybernetical physics. And here, there are no conservation laws. Here we have transformation laws. What is possible by this or that kind of control? How we can change the properties of the system. This is interesting for this area. And if the system is pacifiable, it does not mean that it is passive initially. Initially, it is not passive.
But
And
after pacification, it is passive.
yes, but if we insert some signal, this signal may carry some energy.
Certainly, but maybe no other energy can be brought in the system from inside, only from the outside with this control signal.
I'm not sure. Why not? It can also have some energy sources inside, but by means of control, this we can, how to say, make it behave like system without internal
energy sources. Yeah, thank you. And
Yes.
maybe could you identify some further of this term, pacification, when it was introduced into scientific usage, and by whom?
Yes, actually, it's an interesting story, and it's a long story. The term was not introduced before beginning of 90s, when we were working with David Hill in Australia. And we needed some term to denote this property that system can be made passive by means of feedback. And we introduced actually this term with David Hill, and one motivation was that it looks like identification, pacification, and identification. And another explanation is because we were on the staying near Pacific Ocean. Later, Peter Kokotovich used the term passivation. Maybe it's maybe more convenient because more short. But if you count the number of usages, these terms in Web of Science, for example, pacification is more often. But the meaning pacification and passivation is the same, I think.
Thank you.
Okay, I think those questions are answered now, and we can continue with the presentation. So I think, Boris, you can now take over.
Boris,
can you share your screen?
Share your screen, please.
Okay. Okay.
Okay, great.
Hello. Thank you for attendance. Let me please continue with our presentation, giving some engineering examples. At first, the adaptive coding procedure will be described because it is used for many examples. Then such examples as state estimation of the mechatronic setup of quasi-large helicopter benchmark, and adaptive coding procedure estimation based on the in-flight data from the quadrometers, and state estimation of spatially distributed system with quantization of the transmitted data will be considered. At first, I would like to warn that the most of examples deal with offline data transmission, but the data have been obtained where the experiments. First, adaptive coding procedure. As Alexander told, code a false deviation signal and discretize it with a given M coder range. And the discretized signal is transmitted over the channel to the decoder. Some centroid may be used in the case if there is a bias in the transmitted signal. If its mean average is close to 0, centroid may not be used. Quantize the range is changed adaptively by the following algorithm. Lambda is moving average of the received or transmitted signals, and dependent of its value, zoom in or zoom out stage takes an effect. Here, rho means decay parameter. M0 is initial value of the coder range. M is lower bound, and the coder uses the same algorithm to restore the transmitted signal. Again, the physical examples are listed here. And let us start from state estimation of the multimedial Mechatronic setup. This is a photo of the change of 12 pendulum sections and the motor, which makes a torque for swinging pendulums. The following modified state estimation scheme was used. Exogenous plant model is taken instead of the autonomous one because U is external input applied from the electric motor. We have no information about its generator, how it's generated. So we transmitted it by the separate procedure. For other variables, the following embedded observer has been used. Here, tilde U is measured exogenous input, which is transmitted over the separate procedure. And epsilon is transmitted innovation signal from the embedded observer at the source side and embedded observer at the corner. Chain of 4 pendulums was considered. 5 pendulum angles, U, angle of motor rotation. Following sample time has been studied 10 or 100 milliseconds. This is a binary coding procedure with different number of transmitted letters was taken from new 0, which means binary coder, till new 8. So the first order coder was used for transmitting the motor rotatory angle, and the full order coder with a better observer for transferring pendulum rotary angle. This plot shows dependence of the relative transmission error versus transmission bit rate, depending on dimension of vocabulary. New. It is shown that the binary coder is optimal in the sense of data transmission rate. And for full order coder, exists a threshold which limits the admissible bit rate for data transmission. We can see that data transmission error increases very fast when the data transmission rate is not large enough. The other example is state estimation for quantization helicopter benchmark. The photo of this benchmark is shown in this slide. The helicopter has a base with a longer arm carrying the helicopter body. The arm can tilt on an elevation axis and swivel on the vertical travel axis. Two motors with propellers are mounted on the helicopter body. For this setup, adaptive coding procedure was employed. The state estimation error is calculated and coded by binary coder and transmitted over the channel. Then quantizer range has been changed during the adaptive coding procedure. The embedded state observer was used for coding and decoding procedure. Theta hat and omega hat estimates of pitch and pitch angle rates. L1 and L2 are observer gates. It's assumed that the sensor mounted on the plant is complicated one. So observer may be included into to the sensor side. Some time histories are shown on this slide. Data transmission rate is 10 bits per second, and the error between real and estimated angle theta, pitch angle, is shown by the green line. Process of adaptive tuning of the quantizer range is shown on this plot. We can see that this range increases at the stage when there is fast changing of the transmitted signal, and it's small when the transmitted signal changes slowly. The second example is adaptive coding procedure examination based on the in-flight data of quadricopter. Two quadrators have been employed in the leader-slave formation. The leading quadrator has been governed by the commands from the remote operator's computer. The slave controller was constantly followed the leader based on the leader's position information, obtained through a telemetry channel with a small data rate. The GPS receivers were used to obtain current quadrotor's positions, and XB modulars have been used for data exchange between the quadrators. Flight terrorist area is shown on this Google map. It's not far from the St. Petersburg University. This is a view of the quadrator used for experiments. Again, adaptive coding procedure with binary coder and embedded observer was used, examined based on the flight data. The following parameters have been taken. Sample time was different for different simulation runs, which corresponds the data bit rate 140 and 25 bits per second. Also, observing gain matrix was chosen to ensure given distribution for the discrete time system. Time history of measures and estimated leader coordinates in latitude and longitude are shown in this plot. We can see that if data transmission rate is about 25 bits per second, the error is negligible small. This plot shows adjustment of the code range, which is changing adaptively. Range for the latitude and range for the longitude. Actual and estimated leader trajectories on the horizontal plane are shown in this slide. This is a starting point, and it's seen that some tensor time is needed to reduce the the position estimation error, and then process goes smooth enough. The next example is state estimation of spatially distributed system with quantization. The following wave equation was considered. So this is the initial boundary conditions, and measured output is some inner point along the spatial coordinate. The problem is to estimate chain behavior based on sampled and quantized measurements of Y. For doing this, the partial differential equation was approximated as following a linear fine dimensional system by uniform splitting into k-subintervals. Usual procedure for spatial discretization. And this is the following matrix of the discretized system, and following the following block matrix of the discretized system. For data transmission, the full order coding decoding procedure with embedded observer was used on the coder side and on the follower. Adjustment of coder range was governed by adaptive zooming procedure, and vector zeta serves as an estimate of client state variables in the specified nodes. Some simulation results are shown on the slide. We may compare real and estimated process from some sections along the spatial coordinate. Lower plot is the estimation error between real and estimated processes. Measured output, then its difference tends to 0 between estimated and real measured output. And this plot shows how quantizer range is changing. Generalized accuracy index, maximum of the estimation error magnitude at the interval, some time interval versus data transmission rate, is shown on this slide. And we can see that the threshold is about 40 bits per second. After that, the transmission error is acceptable. After some transmission time, the estimation error falls to 10% range in magnitude of recovered process. M automatically increases during the transfers and decreases in the steady state mode. The limited data rate when state estimation is possible is about 35 bits per second. Accuracy doesn't increase if data transmission rate is greater than 80 bits per second. It's explained by discretization of the initial equation on spatial variable. And which shows how the estimate tends to the real process. Estimate is green line, real process is blue line, and point and circle measured and estimated outputs. So we can see that after some transition time, accuracy is acceptable. I think that's all. Thank you very much.